Hey class, it's just me, Mr. Wee. Sorry for this drawing setup, but all I want you to really do is go to my website. You should download the month 5 cover sheet, and then on the right hand side, well, this is gonna get cleaned up. So this was recorded in 2018. So for my 2018-19 class, please be aware I wrote this in red. That right now the way the month 5 section looks is a little bit disorganized. So hopefully, if there's any other future classes that are watching these videos, you'll see the end result of this being a little bit cleaned up. But what I want you to do is open up this worksheet and notes. 5-5.6 related rates. There's a key to the answers here too as well. So this is what you should see when you guys open it up. And then on the first page, so on the right hand side, I'm going to have this kind of simultaneously, this window on the right hand side open for you guys to kind of follow along. I'm going to do the work on one side and leave the questions on the right hand side where I'm pointing with my Sharpie. Okay, so on the first page I want you to write this. Okay, I know it's a little hard to read. Maybe I should full screen this briefly. Okay, so it's just a reminder of what implicit versus explicit differentiation is. So if I were to take the derivative of this equation, x squared plus y squared equals L squared, with respect to the independent variable being x, then this is how I would do. I would execute the differentiation of each of these variables. So this one would be x squared. So it'd be, this is explicitly a function of x. So that's what I wrote. This is explicitly a function. Sorry, I'm going to rewrite that. A function of x. Okay, and what the function would be 2x, and then you can even multiply it to times dx. So because after you do, like, it's sort of like taking the derivative of the outside function, x squared, or whatever the variable is squared, you would have to take the 2 in the front of the variable, and then essentially you'd have to subtract 2 or 1 from the exponent. So you'd have 2x technically to the first power. Then if you look at x now as another, you took the derivative of all the outer stuff, right, around x, now you actually have to take the derivative of whatever is on the inside function. Remember, the derivative of the out times the derivative of the inside function. Well, the derivative of that would be the derivative of x literally with respect to x. And if you think about that, the derivative of x with respect to x, the derivative of x is just 1. So it'd be like 2x times 1. Okay, so you're asking me, why the heck did I explain it like that? I've never really remembered learning it like that. It makes more sense when I show you something that is implicitly, y squared is implicitly a function with respect to x. In fact, L could also be, could also be a function that has x within it, or is implicitly a function with respect to x. This is, so x squared is explicitly, you can clearly see the equation that explicitly expresses x. Y squared might have an equation within y that has x in it. Like, it could be y is equal to x plus 2 squared. I don't know what it is, but y could be equal to some equation that has x in it. So could L. So that's why we call implicitly a function with respect to x. You do that, you look at y and L that way. As soon as you say take the derivative of all of these guys with respect to the fact that x is the independent variable. Okay, so the derivative of y squared would be 2y, right? Or it would be, you'd have to do the power rule where you would take the 2, the exponent, put it in front of the whatever you're taking, the variable, the derivative you're taking, then you take 1 away from the exponent, so you'd have 2y. That's the derivative of the outside function, and you look at the fact that y within y could be an actual function that contains x in it. So that'd be the derivative of y with respect to x, and that is not 1. Okay, you just leave it like that because you don't know what y is actually equal to. Here, the derivative of x with respect to x is literally just 1, because we were talking about x being the independent variable. Again, x being the independent variable here, you cannot say that the derivative of y with respect to x is simply 1, because within y itself could be a weird function that has x contained in it. We don't know, so we just say that's literally the derivative of y. The same case goes for the L. The derivative of L squared would be 2L to the first power times whatever the derivative of L is with respect to x. Again, I said whatever L is, the derivative of whatever L is with respect to x. That, again, I don't know what L is explicitly equal to. It could be L is equal to the square root of x plus 2x plus x cubed. I don't know what it is, okay? So, and I even wrote a little blurb. You can copy this down too. We need to say this since it's not explicitly stated that y and l are functions of x. Or, I'm sorry, or what the functions of y and l are. So, okay, that's a little old artifact of previous years I've taught. So, it's a little, what is it? Not perfect in the way I wrote it. Okay, so let's have this here. Let's cover this up, okay? All right, so I'm going to be going back and forth between. Dang it! Sorry, it's. Hey, this is not what I want. Come on. I'm gonna spend half this video trying to get everything just taped right. This is annoying. Okay, sorry about that, guys. All right, so oh man, I just hit the stupid camera. All right, let's go down to the first class problem. So we're gonna do what's called related rates. Okay, so how do these problems work? We're gonna start this in 5-6, but the first class problem is assume that oil is spilled from a ruptured tanker and it spreads in a circular pattern. That's very key right there. It's a circular pattern with a radius that increases, a radius increase at a constant rate of 5 feet over seconds. How fast is the area of the spill increasing when the radius of the spill is 25 feet? Okay, so I did go over implicit differentiation and derivatives because those are two things you're going to have to kind of go over and talk about. Or two things that we're going to kind of cover in today's lesson. Okay, so the first step to solving these type of problems, you don't actually have to do step by step, but it really helps if you follow this. So the purpose of this worksheet is to really give you a guideline, like step-by-step guideline, how to approach these problems. You don't literally have to do step 1, step 2, step 3, show me step 4, show me step 5. Okay, it's just a procedural way to kind of deal with these problems that involve derivatives, I don't know, like geometrical shapes. So this whole chapter is dedicated to just that, what we call related rates. Okay, so the first thing you want to do is variables. You have to define variables, what they mean. So if you remember from my first example that I kind of talked about here, I have many different variables here and I took the derivative of them. That's a clue as to what we're going to do right now. So let's take it back. Let's read this one once more. Assume that an oil spilled from a ruptured tanker and it spreads in a circular pattern with a radius. So on the right-hand side, I'm going to start writing the work. So I'm going to say for step 1, hopefully you can see that for step 1, I'm going to say that R is a variable we might want to know, and that's the radius of the spill. Okay. What else do we know? What other things do we know as well? One thing they didn't say is that time is a factor. So, because it's asking me, assume that the oil spilled with a rate of 5 feet per second. So t will end up being a actual an actual variable that you have to consider. It's time, and then the time is in seconds. So that I'm going to define it within seconds. Okay, what else do we see here? Okay, assume that the oil spilled with a ruptured tanker spreads in a circular pattern. So think about it this way: we got circular pattern, and we have a radius that's increasing, but yet it's spreading in a circular pattern. How fast is the area? So area right there, that should tell you right there that we're also looking at A is equal to area of the spill. Again, on these type of problems, you do not have to write all this, but it really helps to see what you have. Okay, so you're going to see how this all kind of coalesces beautifully. Sorry, so step 2 is what are the rates of change? What are the rates of change? So let's see, the rate of change, let's take a look here back in the handout. Let's see if there's any rates of change or things that are changing at a certain rate. Okay, assume that the oil spilled from a ruptured tanker and it spreads in a circular pattern. That doesn't really tell me any rates of change. I think you guys already might see it. whose radius increases at a constant rate of whose let me read that one more time in a different with a different inflection. Okay, the oil spilled from a rupture tanker spreads in a circular pattern whose radius increases at a rate of 5 feet per second. So let's go over here. I'm looking at a change of the radius. Let's see, and it's with respect to what? It's with respect to time. Okay, how much time does it take? So how are we going to write a change of radius? Okay, with time. You're considering time in this kind of thing, right? And really, we're gonna. I don't want to get too far into it, but how do you express that as a change? Well, we know that radius over time is a slope, right? So that's good. So we can think of it as a slope, but don't write this down. Don't write this part down. The radius slope would be like how, what is it? How the radius r changes over how time changes. But in the context of, in the context, let's go back to radius really quick. Let's define the unit. It was feet, okay? And then the area of the spill would be, the area would be feet squared. It's really good if you keep track of the units, all right? So let's go back over here. The slope is radius, how r changes over t. So that's going to give me feet squared. Again, you don't have to write this part, but what I do recommend that you write is that how do we express slope here in the context of calculus? Well, we didn't, remember, we're not talking about slope how it's like between 2 points. We're talking about one particular slope at one individual tangent point. We know that as a derivative. So in the context of calculus, we define not as a slope of r over t, but we define it as the derivative of r, a change with respect to time. Okay, and you can kind of look at it as r over t. You can kind of see the derivative of r. It looks almost as if it's a change of r over a change of t anyways. Okay, and remember, this is basically derivative of anything with respect to some other variable. Basically tells me how something changes. Like if we look at a graph, right? Slope, the way we originally did it was we'd find the slope between 2 points, right? But in calculus, we've advanced that technique to find the slope at one individual point, and that's called a derivative. So we're looking at the rate of change, okay, of the radius with respect to time, and then do we actually know what the value is? It says right here, the radius increases at a constant rate of 5 feet per second. So let's write 5 feet per 1 second. You can write it as per 1 second or just 5 feet over second. 5 feet seconds, okay? Is there anything else we know? Well, let's see. How fast is the area increasing when the radius of the spill is 25 feet? Okay, well, let's see. It looks like, oh, I think I missed something here, but look, how fast is the area increasing? So we're talking about how, like, the rate at which the area is increasing. So we're not just talking about dr over dt. We're also talking about how the area, or how the rate of how the area is increasing or decreasing with respect to time, right? So that's sort of what we're solving for. And I missed one piece of information where it says the radius of the spill is 25 feet. So back up here is where I originally had the radius, which was 25 feet. So it's good to kind of write that out. Okay, so I have a few bits of information so far. I got 25 feet, I got time here, I got the area of the spill, and I also find that dr over dt, I have a constant derivative or value or rate of change of radius at 5 feet per second. I need to find dA over dt, okay, how the area is changing. Okay, so let's read this one more time. We still have to talk about, assume that the oil spilled from a rupture tank. Okay, actually, let's draw a picture. Why not? Draw a picture and find an equation relating the variables only in step 1. So let's think of it. So step 3, I don't have to draw. Again, you don't have to do any of these steps in sequential order, or any of these steps for that matter. I just think it's a really organized way to do this. Step 3, Draw a picture of what's happening. Assume that an oil spilled from a ruptured tank spreads in a circular pattern. So let's do that. I got an oil spill right here. It's spilled, right? And it's a circular pattern, but it's ever so increasing, right? In a bigger circular pattern. Okay, it's increasing at a constant rate of 5 feet per second. So let me see. Okay, so it's increasing. So this dr over dt. It's increasing constantly at 5 feet per second. And let's say that at this radius right here, this is a radius of 25 feet. You don't have to draw this. I just think it's really handy to draw this. Let's see if I can. Oh, no, that zooms in. Okay, that's about 25 feet, right? And what I want to find is how. Let's see. I think the question is how fast is the area spilling when the rate. So right here, I want to find what is the change of the area? What's the rate? Like the rate of the area is increasing, changes at every interval. So what's the rate look like when it finally reaches a radius of 25 feet? It might keep going on and on forever, right? I don't know. It might go to like 50 feet, but I'm looking at particularly at 25 feet of radius from the spill, I guess, or from the origin of the spill. It might even be here. I'm sorry. So might even be here from the origin of the spill. Okay, what's the area? What's the rate of the area that's at which it's changing? What is it at that particular moment where it hits 25 feet? Okay, that's the situation. But let's make a simple equation relating the variables in step one. Okay, and what I mean by equation is what's the shape that we're looking at? We're looking at a circle. So give me the area of a circle. What's the equation of the area of a circle look like? It's pi r squared. Is that not an equation that relates to, what is it? R? Let's say R, A. And it doesn't really have T in there, okay? But it will, right? Okay, so wait. What I can do is I can say this. I have the area is equal to pi r squared, right? What I could do to relate T is like, we're not just looking at the area area is equal to pi r squared, but we're also including the fact that we're talking about the rates of changes too with respect to what variable? Time. So why don't I take the derivative with respect to t of this equation? A is equal to pi r squared. So that actually involves t, which is the other variable in here that we're kind of looking at. Okay? Up here. Okay, so that leads right into step 4. Okay, step 4. And step 4, let's go back on the left-hand side of this. Differentiate the equation from the previous step. So I have this. The actual equation we're differentiating is A is equal to pi r squared. Okay? And I'm going to take the derivative of that with respect to time of A is equal to pi r squared. And let's do implicit differentiation, okay? So the derivative A would simply be 1, okay? But then you have to take the derivative, implicit differentiation, so it'd be 1 times dA over dt is equal to, that's a constant, so if you're taking the derivative over here of pi r squared, the rule is anything that's constant, pi is technically about 3.14, so that's a constant value to me. So let's rewrite this again. Be dA over dt is equal to pi times d over dt of r squared. All right, and what this would look like would be dA over dt is equal to pi times 2r, right? And then because r is not explicitly a function that has t in, like explicitly shown, you have to say 2r times dr over dt. Okay, I'm going to pause right here, and then I will continue in part 2. Thank you guys very much.